Okay, so in section 4.5, we will be talking about applied min and max problems. And up to this point, we've basically been talking about or discussing what we're using the derivative for in terms of a function, but this can also be applied to real-life scenarios. And I'm going to talk to you about some procedures that we recommend you go through, as well as some terms that would be synonymous to help you identify what exactly you're looking for. So before I get started with the steps, we'll talk about some synonyms for maximizing and some synonyms for minimizing. Okay, because it's not always going to say find the max and find the min. So you might see for maximizing, you might see biggest, largest, greatest, longest, widest, furthest, farthest, furthest. Okay, you get the idea, I hope. So this would be for maximizing. Now, based on these, some possible synonyms for minimizing would be smallest, shortest, closest, cheapest, or least expensive, and so on. Okay, so when you're reading these word problems, these are some words that you could take a look for. So this is also known as optimization. And typically we spend 2 days on this, but we're going to focus on the typical types of problems that you might see. So some procedures for solving the applied min and max problems. We have a series of steps. You won't always use every single one, but you might want to just make a checklist for yourself. All right, so what you want to do is potentially draw or sketch an appropriate figure and make sure you label the quantities that are relevant to the problem, because remember, sometimes you can have miscellaneous information. Then you want to identify the appropriate formula for the quantity to be maximized or minimized. Okay, so what this means is we might be looking to see, do we need an area formula or a perimeter, a volume, cost, distance. So you need to make sure that if you're highlighting or underlining, you're going to pick out the appropriate words that are going to give you those clues. Then, using the conditions that are stated in the problem, you want to make sure that you eliminate variables, okay, that don't have anything to do with the problem or that express the quantity to be maximized or minimized as a function of one variable, okay? So as a function of one variable. Then you want to find the interval of the possible values for this variable from the physical restrictions in the problem. So you might be given restrictions, maybe what is the maximum length or height or width. So you need to make sure you underline that. And then, if applicable, use the techniques of the preceding section to obtain max and mins. Okay, so you may have to use, there is the possibility of the first or the second derivative test, but since we did not focus on the second derivative test, we won't even talk about it. So here, in this first example, this is very basic. It says find a positive number. Okay, so we know that our answer has to be positive, such that the sum of the number and its reciprocal is as small as possible. So the sum of the number and its reciprocal is as small as possible. All right, so in this case, we're looking for a minimum. Okay, because of this, we're looking for a minimum. All right, okay, so when we take a look here, it says, just pretty basic, we want a positive number such that the sum and its reciprocal are as small as possible. So we know we're going to be using addition. The issue here is we don't have any variables, so we need to designate. So we're going to say let x be equal to a positive number. Okay, so once we do that, we know that 1 over x is equal to the reciprocal. Now, again, you could pick any variable, but typically we pick x. So we're going to say that the sum is equal to x plus 1 over x. Now, when we're determining a min or max, we're going to take the derivative with respect to x. So what we actually need to do is write this in friendly form. So we're going to rewrite this as x is equal to x plus x to the negative first power. So now we can take the derivative of the sum with respect to our x variable. So we have ds dx is equal to the derivative of x, fortunately for us is just 1. The derivative of x to the negative first is negative x to the negative second, which is 1 over x squared. So we want to write that in a form that we can actually use. Okay, so what this shows is our independent and our dependent variable, and in order for us to do our test, what we have to do is get this as one fraction, which means we need a common denominator. So when we do that, we're going to get a common denominator of x squared, which means this would be x squared over x squared, which is 1, minus 1 over x squared. So now, in order to get our critical numbers, I'm going to move this up here, we're going to set this rational function equal to 0. So we have x squared minus 1 over x squared is equal to 0, and this is to find our critical numbers to test on our number line. Okay, so we can factor this numerator, x plus 1 times x minus 1 over x squared is equal to 0. Now remember, to get critical numbers from a rational function, you set both the numerator and the denominator equal to 0. It doesn't matter that this is a vertical asymptote, it's still a critical number. So we have critical numbers of x being equal to positive 1, negative 1, and 0. Now at this point I know you can eliminate some choices here based on what we're looking for, but you actually do need to complete the test. So what you're going to do is take a look on our number line, okay, and we have negative 1 here, we have 0 here, and we have 1 here. Now, because the problem says we want a positive number, we know that this is out. 0 doesn't have a sign designation, so we know that this is out. So 1 has to be our option, but we want to make sure. So really we just want to test here. So if I were to pick 2 and plug 2 into either the factored or the non-factored form, 2 squared is 4 minus 1 is positive, 2 squared is 4, that's positive, so this interval right here is positive. If I were to pick, let's say, 0.5, 1/2, 0.5 squared is 0.25, minus 1 is negative, 0.5 squared is positive, so that means this is negative. So to prove to you that this is a minimum, remember, this plugged into f prime indicates the direction of f, meaning that f of x is decreasing on this interval and increasing on this interval, indicating that this would be a minimum. So you would say that s has a relative min at x equals 1 because, and here we use the notation ds dx, ds dx changes from negative to positive. Now this right here is your justification, and we're just practicing going back to what we learned before you guys went on break. Okay, so we found our value where x is equal to 1. Okay, there's our justification if we needed it, and we're done with the problem. Moving on to this second problem here, we have a series of pieces of information that we're going to need to use, and this actually goes back up to these steps here, which is more applicable than the first problem. So we have a farmer that has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. Now I know a river is never straight, but we're just going to take them at their word. He needs no fence along the river. So what are the dimensions of the field that has the largest area? Excuse me. So let's highlight some important information here. So we have a farmer that has 2,400 feet of fencing. and he wants to fence off a rectangular field. So we know we're dealing with a rectangle, okay, that borders a straight river. So he does not need fencing along the river. So that really means he only needs 3 sides, okay, and we want to know the dimensions. So that's going to be length and width for the largest area. So I would ask you, is this a max or a min? Largest would indicate a maximum. Okay, so this is what we're looking for. First of all, if we have this river here and this farmer wants to create a rectangular fenced off area, okay, remember you're not filling this in, so we're dealing with the perimeter. So we know that the perimeter here, if we call this y and we call this x, it's really only going to be x plus 2y. Now guys, it doesn't matter if you call this x and this y, it makes no difference. Okay, as long as you indicate which one you only have one side of. Doesn't make a difference. Okay, and they said that the perimeter is 2400. So this right here is 2400 is equal to x plus 2y. Okay, so we have some important information here, and actually we could solve this for x or y, but we'll see what we need. So now we want to maximize the area, and we know here we have the area of a rectangle. If I said that this is x and this is y, we're going to say the area is equal to x times y. Now the problem here is that I don't want 2 variables. I'm going to take the derivative of the area with respect to 1 variable. So that's why I need to go back to this perimeter. You make a choice. What is the easiest to solve for? In this case, the easiest to solve for would be x. So I'm going to say that x is equal to 2400 minus 2y. So what I can then do is plug that in over here and eliminate one of these variables. So I actually needed 2 formulas here. So now we're going to say that the area is equal to y times 2400 minus 2y. Now, just like in the previous problem, we know we have to take the derivative, but to make our lives easier, I'm actually going to distribute this so I don't have to use the product rule. So the area is equal to 2400y minus 2y squared. So now I can take the derivative of the area with respect to my y dimension. So it's dA dy is equal to 2400 minus 4y. Now, just like before, we have to obtain our critical number or numbers. So I'm going to set this derivative equal to 0. 2400 minus 4y is equal to 0. Add 4y. And divide by 4. So we're saying that y is equal to 600. And more specifically, this would be 600 feet. But remember, we want to maximize. So let's test and see what happens. So if I throw this critical number on a number line, we know that our minimum would be 0. Here we have 600, and this is going to an infinite value. So remember, you're plugging back into your derivative. So if I were to pick, I don't know, 1, 2400 minus 4 is a positive number. And let's say I were to pick 700. Pick something easy. 4 times 700 is 2800. So 2400 minus 2800 is going to be negative. So remember, here we're increasing, here we're decreasing. Therefore, this is a relative max. Now again, this is not any kind of justification. It's just proof or verification for yourself. So if we know that y is equal to 600 feet, we can turn around and plug this in up here and get our x value, which is our dimension, which in this case would be 1200 feet. Okay, so here are the dimensions. If I had to justify, I could say by the first derivative test, okay, area has a relative max at y is equal to 600 feet because dA dy changes from positive 2, negative. This is if you had to justify how you got your answers. Okay, and those are your two applied problems.